But first to start, like my personal interest in research is about developing autonomous systems that operate in complex human environments. To me, humans are the ultimate challenge for robotics. They're messy, they're diverse, they're entirely unique. They each have their own preferences. And these differences and diversities are just such a great challenge for robotic systems. In particular, with the work I'm going to be talking about today, the subset of that work we're interested in is how do we leverage semantic reasoning to achieve more robust autonomy? How can we make robots more intelligent through this mechanism? And so to start on that, what is semantic reasoning? What is semantic information and so on? And depending on the field, semantic information can come in slightly different forms. If you're in computer vision, it looks like this, right? Where you're extracting semantic information from the scene and not only recognizing a horse and a wagon, but actually identifying the fact that these horses are Clydesdales, they're pulling the wagon, not just standing there, and the men are riding inside it. Within robotics, you can have semantics at other differing levels. You could think about semantics of space. What is a hallway? Which, X, Y coordinates correspond to a hallway versus an office space. You can think about objects either at the entire kind of visual scenes of surfaces and chairs, or you can drill down and look at a specific object and look at the semantics of that object. For example, this cup has a grasping portion that you would hold and then a contained part that actually has the liquid. And that's really cool. And these are all examples from other people's work, just to kind of set the scene for what we're talking about when we're talking about semantic reasoning. And as a general definition, what I mean by the semantic information is it's a type of data abstraction. Fundamentally, anytime we're talking about semantics, we're talking about taking raw level data, so pixels, XY coordinates, images, and abstracting them. And we typically assign word labels to that abstracted data, and that these word labels represent concepts, facts, ideas, or beliefs about the world that enable us to generalize information. And this idea of word labels is actually really important because what we've done is now we've taken low-level sensor data, we've made it accessible through language to humans. So not only is it more interpretable, but we may be able to use it to communicate with users as well, which is something I'll touch on at the end. And then finally, so that was all about semantic information when we're talking about semantic reasoning. Typically, the goal here is to draw new insights, to generalize in some way, to figure out something you didn't know before based on the semantic information you already have. And so, this is kind of the space that a lot of people are working in right now. This is a space that I'm going to talk about 3 different projects very quickly over the course of this talk. I'll try to leave time for questions, but if you have a question as we're going along, I don't really see the chat right now, but you're always welcome to unmute and hop in and ask me anything. All right, so now diving in a little bit more deeply into semantic reasoning. In most of the literature so far, semantic information is represented in the form of something called triples. If you haven't seen it before, it's very intuitive, right? You have something called a head, a tail, and a relationship between them. So fork is a utensil, fork is made of metal, and so on. And so we can encode lots and lots of semantic information in the form of these triples. Now, to actually learn based on this data, what typically happens, before I get to that, the typical query, if the left side is all the known information that we know about forks or utensils, we know spoons are utensils, we know spoons are made of metal, and so on. A typical query, right, for reasoning might be about something you don't know. Are forks more likely to be found in offices or kitchens? Now, this is not a triple that's in our list on the left side of the slide, and so we have to infer it. Now, typically when we encode this in machine learning, most recent methods use neural networks of some sort. They take each of these concepts, they embed them, right, in high dimensional spaces, and then develop a machine learning system that learns a mapping in order to predict new knowledge from known knowledge. And so here you would potentially train a model to say, since forks are similar to spoons because they're both utensils and spoons are located in kitchens, then it's much more likely that the fork is located in a kitchen than an office. It's not quite that level of causal reasoning because this is very much just a neural network, which is a little bit more of a black box. But this is the kind of techniques that are out in the community right now. And again, I'm citing just a general concept from other people's work. All right, now I'm going to start talking about our work and how we've connected to this kind of representations in order to do a few different things. I'm going to talk about first, modeling objects and object grasping, and how do we reason about robotic tasks, particularly relating to manipulation. I'll talk about going beyond binary relations to more complex relations, and then I'll talk about explainability as well towards the end. All right, so this first project, as I said, is all about semantic grasping. And just to define that, what we mean is that we're not just trying to do a power grasp. We're not just trying to get the robot to pick something up. We want to pick it up in a meaningful way. If you think about humans, when we pick up a pen, we pick it up very differently depending if we're going to write or if we're going to hand it to somebody. And the same goes for many other objects. If the object is hot, we handle it differently. If it's clean or dirty, we handle it differently again. So the challenge is, if you know what task you're doing and you know the state of the object, how should you grasp an object? And there's again been prior work in this area. Some of it has been very vision-based. So for example, the fast point feature histogram method. And there you're looking at visual features of the objects in order to figure out where to grasp them. This works, but is really, really hard to generalize to unseen objects, just because of the diversity. You can see just the bottom row of this picture. Each bottle looks very, very different. So you need a lot of training data in order to generalize this method. Other people recently have looked at rules. They said, maybe this isn't, we don't need to do this kind of so data intensively. Maybe we could just have categories. This is how we teach kids. If the object is a spatula and the task is to lift something, then you should grab the handle, and otherwise you shouldn't. Maybe this isn't so bad. The problem is that once it gets really complicated and you have a lot of different objects in a lot of different states, this is a picture of our most recent data set. What happens is that you're going to need hundreds and hundreds of rules. And so this becomes, for our data set, it would be about 780 rules, I think, that we'd have to write by hand. So that's a lot of work. So, you know, so maybe some common ground there. Or some in between, you know, rules have certain uses, but maybe not exclusively. All right, so when we decided to tackle this problem, we did want to be bottom up. We wanted to reason about data, but we didn't want to just reason about visual data. We wanted to reason about multimodal data, many different modalities, going beyond just vision to material properties, to state of the object, and so on. And so that's the technique I'm going to talk about today. It's called CAGE, Context-Aware Grasping Engine. And we talk about context as all this other information that our system reasons about. The data set we used, there wasn't really a data set for this that was particularly large. We released 14,000 grasp data set. Actually, a few months after this paper, we released a much larger data set again. So if you're interested in semantic grasping, do take a look at CAGE. And then it's, I don't think we named the later one, but there's another one that WayU is on. All right. And so context, as I said, already kind of interested in this idea of having a diverse context to drive the reasoning of the robotic system. So we're going to tell the robot the task that you're going to be scooping, for example, or just handing something over. That information is given. We're going to tell the robot the state of the object, such as it's empty or clean. And here for this project, we're going to cheat because we don't actually know from sensor data how to detect whether something is empty. In the next project, I'll talk about how to fill in that missing data. But for now, we're going to give that from the user, and everything else the robot's going to detect by itself. It's going to use the camera to get both 3D and RGB data, just so color data, and it's going to get material properties automatically using the spectrometer from a company called SIO, which I'll explain in a minute as well. And so I'll just show you how this works step by step, how we acquire for a given object and a given task, how we acquire all this information. So here the goal again is to scoop using this ladle, and the ladle is empty. And so then the robot observes the scene and says, okay, I recognize the spatula. So this is from image recognition. And then we apply a method called affordance net from other researchers that segments the object into meaningful affordance parts. And this is really cool because it allows us to think about the grasping portion and the support portion. Again, not our innovation, but the authors are listed at the bottom of the slide. Very cool work. And what it allows us to do in particular, this is not the only segmentation method out there, but the one we like using is because it generalizes so well across objects. You can see kind of at the top row here, all of these objects are some sort of container. They have slightly different shapes, colors, whatever. But you can see that at a high level, they all have a thing you would pour into and a thing you would hold. And that allows, that level of abstraction allows the robot to generalize really well to things it's never seen before. Same thing on the bottom. So that's really cool. And so now we have object name, we know what parts it has. And here's a video of the robot getting more information. Here it's using a handheld spectrometer to classify the material properties of the object. And a spectrometer just gives you kind of a large array of data using a spectroscopy mechanism. And you can train an LSTM to classify material properties from that. There's a nice RAL article on that. Really cool sensor. For anyone interested into getting into this kind of stuff, I think it's like $300 for the spectrometer. It's been super, super cool to play with and gives us ability to more or less in real time detect the material properties of objects, to tell something squishy from something hard. Really, really fun. All right, so that gives us that. What else do we get? Oh, last but not least, we sample the grasps, all the grasps that are available on this object. And this is just an off-the-shelf, again, grasp sampler, lots of options. We use one from Rob Platt's group. But the goal here is now we have ideas. We have about how to grasp the object in order to achieve a power grasp. Now, as I said at the beginning, we're not looking for a power grasp itself. We need a semantically meaningful one, but you do need to be able to pick up the object. And so we sample all the possible power grasps that would allow us to actually lift the object. And now our goal is to rank them based on this semantic context in order to figure out which one's most suitable. Now, to do that, we use a model called the wide and deep model. This came out of Google a few years ago. Somewhat underused model in robotics. It's really nice because it balances depth and breadth, sort of, right? So generalization and memorization. It can do both things. I have an ablation result at the end that shows that kind of having this duality in the model actually does help achieve cool performance. Google uses it for recommender systems. It turns out it's really cool for semantic applications as well. And so the way we train it, is we feed it in this context, right? So all of this information, and then we train it to recognize grasps that are suitable and are not suitable, given a particular context. And then at test time, we provide new queries of object combinations or object state combinations that the system's never seen before. And so the output of the system is a score that tells us the suitability of a certain grasp. And so we're able to take all the grasps that we have for a given object, rank them, and select the one that's most suitable. And so, for example, for this context, scooping using an empty spatula that contains these affordances, and it happens to be plastic. Here is an example of the grasp that the robot decided on, which was reasonable and appropriate. All right, to test this, as I said, we collected a huge data set, lots of different objects, and then we also had different states: hot, cold, empty, filled, lid on, lid off. We had different materials, including stone, paper, wood, and so on. And we had lots of different tasks, including poking, hammering, handing something, and so on. We held out 30% of the data set for testing, which led to the results that you see here. So this is just on this computational results on 30% of the 700 or so, no, 14,000 or so grasps. And you can see that our approach cage is in green, significantly outperforms previous techniques. These are largely the visual, these are the visual methods that I mentioned before when I was talking about prior work. And what this means is really that vision alone isn't going to give you quite the context that you need in order to reason about some of the characteristics we're thinking of here. And this is on the right is the ablation result that says that the wide and deep model, if you cut out either the wide or deep portions, you lose performance. It also shows that if you drop state information or task information, then you lose performance as well. So our model is actually basically using all the information we're giving it. Not crazy surprising, but good to know. And then here's a few videos of how it works. On the left, it's scooping. On the right, it's handing it. So you can see it's holding it differently. These are handing over, but the left one's hot and the right one's empty. Handing over hot on the left and empty on the right. And poking or stabbing somebody with an object you've never seen used for such a task, which is also kind of fun. It figures out to poke with the long end of the object. All right, so that's kind of to summarize this first project. What we're finding here is that more semantic context is helpful. The more information you have, the more the robot is able to reason about really complex factors and kind of combine or reason about the situations that it has in order to reason to generalize to new objects in a reasonable way. Now, here, as I said, we are cheating in one way, which is that we are giving the state of the object. I'd like to talk next about how we can reason about objects in a more complex way in order to fill in some of this missing data so that we don't have to make assumptions about users giving us all the information that's being always very complete, because a lot of the time you're not going to have information about every aspect of the object. All right. Now, prior work, again, kind of digging in a little bit, I talked about triples at the very beginning, right? And triples, despite the name that they sound like they have three parts, they're a binary representation. You're mapping, you're saying, is it true that forks are utensils? Yes. Is it true that forks are furniture? No. Right, and so you kind of have a binary relation between a certain object and a certain property. And this has been studied a lot. This has been applied to visual information, haptic information, auditory, and so on. But it's always in these binary relations that I mentioned. So here's examples from different papers. There's a list of at the bottom. It's just a partial list. Our work has also included mostly these kinds of binary relations. But for many situations, binary representations don't take full advantage of all the different information that's available. It's much harder to train models to do that. So for example, if I see a cup in the cabinet, can I assume that it's either clean or dirty? And to use a human, this is obvious, right? You're going to say, of course, that's a clean cup. It would be crazy for someone to put a dirty cup in their kitchen cabinet. And how do you know this? Because of frequency analysis, right? You've seen basically many cups. You've seen many kitchens, and nobody does this. And so it'd be nice if this kind of, in this case, n-ary relationship, so three-way relationship between a cabinet cup and cleanliness, could be modeled explicitly by the model, right? Here's another example. And so this is kind of an example, and then kind of getting into what I want to propose as this representation. We're going to be moving from binary representations in this project to n-ary representation. so that we can reason more complex interconnected object properties. So for example, here's n equals 4. You have the relationships between cups, locations like sinks and cabinets, material properties, ceramic, and cleanliness, clean or dirty, right? And so if you just know, if someone says, hey, can you bring me a cup? Now you have to figure out the location of that cup. It could be a sink, or it could be a cabinet. You actually don't have enough information. If someone then says, bring me a clean cup, right? So now this is the green, it's meant to indicate given information. If you give me a clean cup, you're gonna say, the cabinet is much more likely. That's the kind of thing we're going for. Again, we're not the first to introduce n-ary relations. There's a really cool community in semantic reasoning that has been looking at that. As far as I know, we're the first to pull it into robotics as a field and to show that it could be useful for the type of data the robotics field is reasoning about. All right. One of the biggest challenges for us as roboticists has been, how do we get n-ary data? This has been surprisingly challenging. It can come in many, many different forms. You could have binary relations, three-way relations, five-way relations, and they all have to have this meaningfulness, right? There has to be, they have to make sense. Or, I mean, I guess we could have made a random data set, but we really wanted to make one that made sense, such as, you know, when I brush my teeth, I'm in the bathroom and I use a plastic cup because I don't have glass in the bathroom. And that cup I'm going to use is now going to be wet and it's no longer clean, really. And it's located in the bathroom, and it's very different from the cups I would use in the kitchen, you know, that kind of stuff. And so we went through a long process of like multi-stage process that I don't have time to talk about here, of crowdsourcing this data. It's like a three-step process in which we would get information like red cups that are thin and short are used for pouring, they're plastic, this one's currently full, it's compressible, it's hot, and it's on the table in the kitchen. Right, so lots and lots of kind of very detailed information about these scenes. And our goal was to be able to answer queries for this type of information. Now the queries we want to answer are incredibly diverse. We want to be able, if someone says, give me a cup, I want to be able to answer that. If someone says, bring me the blue ceramic cup, I want to be able to answer that. Answer that to go for the robot to go find it, right? If I want to say, bring me my hot cup or this cup in the sink or whatever it is, the robot should be able to carry out all of these different things, all of these different tasks. So to train that model, we introduced a transformer-based neural network. The way we train it is by hiding or masking specific constructs and then having it learn them. So here is the blue cup in the sink example. This is, we, for example, mask out the concept sink. We mask out the location, give it all the rest of the information, and we have it predict sink. And you do this iteratively. So you do it for sink, you do this for ceramic, you do it for other objects, and you can predict temperature, not just location or material and so on. So we have like a lot of different contextual inputs again. And when we're testing it, again, we're testing it at very different levels of abstraction. We can ask things like, is this ceramic cup fragile? In which case, in this query, we just give the transformer the material property ceramic, we pad all the other entries, and we have it predict the hardness. We can predict location, right? So where is the full and cold bottle likely to be located? Or we could say, is the cup, the white ceramic cup on the kitchen rack, is it clean or dirty? Right, so we can perform all of these types of predictions. And I don't have time to fully go through the results. I'll go through some of them. There's some fun things we've done with the attention to kind of verify what the model is learning. Here's a cool one here on the bottom for cleanliness. It's interesting to see what the model's kind of using, what it's using to make the prediction, whether the object is full or empty, where it's located, and whether it's damp or not. Are major predictions of its cleanliness, as well as the room location and so on. So this makes a lot of sense from you know, a human perspective, I guess. And similarly for some of these other classes. And so I guess this slide is slightly out of order. I should have mentioned it earlier, but the data set we created is called LINK, Learning Instance Level Entering Knowledge Data Set. In total, it's 15 property types, 200 properties. So property types is like location, and properties are kitchen, bathroom, living room, and so on. Or material is a type, wood, ceramic, and so on are properties. 11 object classes, over almost 1,500 object instances. And so it's a significant data set to go off of. Our results show that we're able to outperform the best baseline. So these are a variety of baselines, but the MLN is the strongest baseline. We do outperform that quite strongly, but the other cool thing to note is that our running time is a lot faster as well, significantly faster than the MLN, of course. And just to show you that we could do this, this is our test set with the robot. We also asked people to do this. This is the dark blue, and our approach is in orange. So we're almost as good as people. We ran people just to show that it's not 100%. For humans, it takes them a little bit, on the first try, second try, third try, humans with 91% accuracy can find an object on the third try in a kitchen that they don't have perfectly mapped out. Our technique is getting up there. It's fairly close, which is really cool. I'm running out of short on time, but I'll just show a couple of videos that the robot is searching for a dry sponge, and it's looking on the counter and in the drawer. And when you tell it to look for a wet sponge, it'll look in the kitchen sink or bathroom shower. So depending on the properties of the object, it'll actually execute different searching behaviors to locate the object of interest, which is cool. So fun. We've had lots of fun with this project. Again, kind of given us a lot of flexibility to reason at a different level of abstraction than we normally get to, and again, more complex scenes. I said that the last project I'd talk about would be on explainable AI, but unfortunately, I'm not going to have time to talk about that. So I'm just going to wrap up in order to make sure the next speaker starts on time. I'll just say that, for those interested in semantic reasoning or haven't yet been, maybe I'm convincing you to be interested. I think going for more rich data, don't be limited by data sets that are out there right now. A lot of them are only text-based. Go for multimodal, embrace the fact that our robotic systems are operating in physical environments. Go for those really different modalities. I think it adds a lot of value to the types of reasoning that our robotic systems need to be able to perform. And reasoning at these different levels of abstraction is also super, super important. The work I just presented was all done by Wei-Yu Liu, who's here on the left. I unfortunately didn't get to, I was a little too ambitious about what I wanted to share today. I didn't get to Devlina's work, but Wei-Yu is kind of the mastermind behind all of the things I talked about today. So big thanks to him as well. All right. Thank you all for listening. I don't know, I'm going to let the organizers decide whether to move on or do something else.
Thank you, Sonia, for a very interesting talk.